Welcome to Team Vessel's Junior Colloquia Defense. My name is Amy Zoe, and tonight myself, Nina Al-Salihi, and Marquis Singletary will be discussing our team's research project, Vascular Electrospun Silk Engineered Linings, and how we hope this will assist in bypass surgeries. So to begin with, we'll discuss the problem that we hope to treat, which is vascular disease, and then we'll explain current relevant research being conducted in the field. We'll go on to talking about our own project and how we will develop and test our graft. We'll then conclude by discussing our possible future directions and a reflection of the team process thus far. But first, a video.
Cardiovascular disease is the leading cause of death in the Western world. It affects 1 in 3 Americans. As a result, more than 1 million bypass surgeries are performed in this country alone. We want to design an electrospun self-fibroid vascular graft with enhanced biochemical and mechanical properties. We are Team Vessel.
We are part of the Honors College Gemstone Program, a 4-year living and learning program designed to help teens advance knowledge and answer society's urgent questions. Team Vessel stands for Vascular Electrospun Silk Engineered Linings. Our project involves extracting silk fibroin from silkworms, electrospinning the extracted fibroin, and enhancing these silk grafts through the addition of specific coatings and growth factors. Our multidisciplinary team consists of 13 dedicated and hardworking students from a variety of different backgrounds.
We've already begun developing our first graft prototype. Creating these grafts requires a multitude of materials, from a batch of silkworm extracted silk to solutions to dialysis cassettes. Your support can make all the difference.
So we're proud to announce that today was today was the day that we raised our goal of $5,000. We have one more day of donating left, so we would really appreciate your support. Thank you. Okay, so just to recap from the video, cardiovascular disease is the leading cause of death worldwide. And to really stress the seriousness of this disease, the top 5 reasons for hospital visits are because of cardiovascular disease. Please keep these figures in mind as we move on in the presentation to serve as a reminder of how universal and severe this disease is, why it is so vital to research it, and why our team decided to choose this disease to investigate. We are specifically focused on peripheral arterial disease. Peripheral artery disease it basically happens when arteries in your extremities become narrow. As a result, plaque can build up along the walls of these arterioles and blood flow can decrease. This can lead to tissue and nerve damage. So, for most patients, typical treatments include diet and exercise, medication, and for more serious cases, arterial bypass surgery. Though it is often the last resort, bypass surgery is the most commonly performed heart surgery across the US and Europe. Basically what it does is it uses vascular grafts to redirect blood flow away from problematic areas of clotting and disease in the patient's circulatory system. So what is a vascular graft? Basically, like I just said, it acts as an alternative path for blood flow away from problem areas, but equally important is how it acts as a scaffold for new cells and tissue to grow, allowing a new native vessel to form. In bypass surgery, autologous grafts are preferentially used. However, there are many circumstances for which this just isn't feasible due to poor tissue quality, lack of available tissue, and other complications. Because of this, engineered grafts provide another option, especially with the growing population of the elderly and increasing incidence of cardiovascular disease. Those grafts, engineered grafts made from biomaterials, are very appealing and very promising. Synthetic grafts or engineered grafts have been developed and successfully developed for large diameter vasculature, but much less so for small diameter vasculature where blood flow is low and much less constant. Small diameter vascular grafts increase biocompatibility, but problems include occlusion, which is the closing of blood vessels, thrombogenesis, which is when a clot that's forming breaks off and blocks another vessel, and other mechanical issues. So the ideal graft would not result in any adverse response from the patient. It would mimic the properties of the native vessel, meaning that it would have the right biocompatibility, compliance, elasticity, porosity to match those of the native vessel. It would facilitate and support the growth of new tissue and recruit cells, allowing for tissue regeneration. And it would also be resistant to any form of clotting and any other blockage. The material we plan on using for our vascular graft is silk produced by the Bombyx mori, otherwise known as the silkworm. In 2007, there was a study done by Lovett et al. Showing that silk fibroin is in fact a viable option for small diameter vascular grafts. It's abundant, it's structurally advantageous, and very biocompatible. So our research question is basically, how can a basic small diameter electrospun silk fibroin vascular graft be biochemically modified to improve the graft's overall patency? And we hypothesize that by adding coatings and growth factors to these grafts, we'll be able to improve mechanical properties and encourage the recruitment of endothelial cells, more specifically HUVECs, in order to foster tissue growth and proliferation. How will we do all this? To elaborate, Mina will explain our methodology.
Thank you, Amy. So our methodology is going to be composed of multiple stages. First, we're going to extract the silk fibroin from the bee mori cocoons, and then we're going to turn this into an aqueous solution. Then we will electrospin this into our basic graft construct, which we will then apply different coatings and growth factors to. Then we're going to do various different mechanical and biochemical tests. So, as we said earlier, we chose silk because it's very abundant and it has excellent biochemical and mechanical properties. So, first, to extract the silk fibroid from the cocoons, we'll do a series of a degumming process in which we cut open the cocoons. We boil them in sodium bicarbonate, and then we dissolve them, purify them, pour lithium bromide over them, and then use a dialysis with ultra-pure water. Our final silk fibroid solution can be stored up to a month at 4 degrees Celsius. So currently we don't have an electrospinner, so we're using a graft dipping process to create our graft. First we concentrate the silk fibroid, then dip a wire into the solution, then we fix this with methanol to create stable metal-plated sheets, and then we repeat this a few times to make it thicker, and finally we remove the wire from the graft. So once we do get an electrospinner, we're going to use this to create our graft. We want to use an electrospinner because it allows us to have more control over the graft composition. Our electrospinner will be similar to the setup you see here, except one big difference is we're going to use a mandrel instead of a collecting plate so that we can create a tubular shape for our graft. We're going to use 3 different coatings on our graft, including fibrinogen, which helps with cell adhesion, heparin, which prevents blood clots, and elastin, which helps with flexibility. In addition, we're going to use multiple growth factors, such as vascular, endothelial, and epidermal growth factors, which both help with slow growth. We're going to use Matrigel as a scaffold to help our cells grow. Matrigel has over 1,800 different proteins, so it mimics the rich environment of an in vivo extracellular matrix. So this creates a basement membrane protein to allow the cells to grow, and it's commonly used in many different applications. So we have 3 different tests for our mechanical properties, including the burst test, which sees how much the graft can withstand blood pressure, as well as a tensile test, which tests the graft's resistance to internal longitudinal stress, and finally our suture test, which uses a DMA machine to test the retention of the graft. And finally, we have biological tests, including our MTT assay to see how much there is cell adhesion in the graft, as well as testing different degradation properties, and a cell cytotoxicity test to see if the graft can even support cell growth. Now Marquis will talk about our current data and future direction.
Thank you, Mina. Thus far in our research, we have mastered silk preparation. We have achieved a tubular structure using dipping method. We have also familiarized ourselves with the electrospinning technique using different solutions. We have tested our control graph with the tensile test, and we have begun our initial preparation to perform the burst pressure test in the next month or so. Using the data from a few of these procedures, we're able to present the following findings with you. So for each batch of silk, nanodrop UV-vis spectroscopy was used to measure the concentration and purity of the silk. This was performed for quality control, and the above is a representative spectrum. Each batch was concentrated to approximately 15 to 16% silk fibroin, and the graph above shows the relative nucleic acid to protein absorbance, which was found to be comparable to the literature value of 0.60 or less, which is the literature value for pure proteins. In addition to solidifying our silk preparation methods, we've also begun testing our control graph for mechanical strength. The above image is a stress strain curve using a DMA Q800, which is the machine used for tensile testing. This specific test used a strain rate of 2.5% strain per minute and ranged from about 0 to 25%, failing at about 17%, as you can see it drop off right there. This data is comparable to the literature, but in order to draw trends, we really have to do many more replicates. Moving forward in our research, we would like to continue with our preliminary data collection, and in the spring we will be collecting more data, hopefully electrospinning, and then we will be presenting all of our research thus far at Undergraduate Research Day. In the fall of the next semester, we will be finalizing all our data collection and analyzing that to revise our thesis, and then in the spring of 2017 we will be presenting that. Okay, some of the challenges that we faced in Gemstone, specifically with all the group work, every group is going to face a ton of challenges. Our biggest challenge has been so far finding meeting times that work for everyone, specifically subgroup meetings and lab times that everyone can go in. In addition to that, holding teammates accountable is something that every team faces as a challenge. And while we've been fortunate with our work ethic, there's always room for improvement in terms of that. And I know you guys have been asked to absorb a lot of information this evening, but we really want you to kind of focus on these key things. Communication is the key to kind of overcoming any obstacle that you will inevitably face throughout this process. In addition to that, staying abreast of the new and potentially useful information that's coming out about your project is crucial to the success of your project. And finding the joy in what you're doing is the best way to produce your best work. So I suggest that if your joy is maybe in bonding with your team or really getting that lab time in, that you do that. You identify that, you communicate with your team, and you really enjoy the process. So again, like I said, with our goals, this is basically our timeline that we're going to be following. We're going to be electrospinning, we're going to be modifying our graphs with cell adhesion and adding matrigel. That will be in the fall, and then we'll present that at Undergraduate Research Day, followed by more data collection, more analysis, and then we'll be revising our thesis and defending our thesis in the spring of 2017. In conclusion, there is a clinical need for a viable small diameter vascular graft. Thus far, we have successfully created a tubular small diameter silk fibroid vascular graft, and we will continue to improve that with the engineering and the modifications and the testing of these grafts. And before we wrap up, we would just really like to extend a huge thank you to our support system. None of this would have been possible without this long list of names that thankfully continues to grow. And in particular, we would like to thank our mentor, Dr. Shea, and we would also like to thank the Gemstone staff, Dr. Full, Dr. Scandal, Leah, Vicki, and Jessica for your continued support. Thank you, and we would like to open the floor for questions.